Hello all, my name is Mekala Vashit Reddy and I'm currently pursuing my BTech at Institute of Aeronautical Engineering at CSC, and my specialization of branch is Artificial Intelligence and Machine Learning. So let us dive deep into the topic, and we are going to be discussing about calculation of losses in laminated ferromagnetic materials. So, in this topic, we are going to see some of the subtopics such as overview of losses in laminated ferromagnetic materials, importance of calculation in material design, challenges in loss calculation. Okay. Introduction to Calculation in Laminated Ferromagnetic Materials. Overview of losses in laminated ferromagnetic materials. A numerical method for calculation of power losses of nonlinear laminated ferromagnetic core is presented. The calculation is made into two subsequent steps. In first step, the approximate magnetic field distribution in material is determined assuming non-laminated bulk non-linear ferromagnetic material with anisotropic conductivity. In second step, the non-linear ferromagnetic material of laminated core is replaced to a material with spatially inhomogeneous permeability. A loss function. Importance of loss calculation in material design. A loss function is a measure of how good your precision model does in terms of being able to predict the expected outcome. We convert learning problem into an optimization problem, define a loss function, and then optimize the algorithm to minimize the loss function. Okay. Losses in loss mechanism in ferromagnetic materials. Hysteresis losses. Hysteresis losses refers to energy losses that occur in a material subjected to a varying magnetic field. These losses are primarily encountered in ferromagnetic materials such as iron and steel, which exhibit a phenomena called hysteresis, eddy current losses. When magnetic field varies, it induces circulating currents known as eddy currents within materials. These currents circulate within closed loops and generate heat due to electrical resistance of material. Excess loss refers to additional energy loss that occur in electrical machines such as transformers, motors, and generators beyond the losses accounted for by hysteresis and eddy currents. Hysteresis refers to energy loss that occurs in material subjected to varying magnetic field. These losses are primarily encountered in ferromagnetic materials such as iron and steel, which exhibit a phenomena called hysteresis. When primarily encountered in ferromagnetic material is exposed to a changed magnetic field, the magnetic domains within the material align and reorient themselves in response to field. However, due to nature of ferromagnetic materials, the alignment of domains does not occur instantaneously or linearly uh, with the field. Instead, there is a delay and non-linear response resulting in hysteresis. Mathematical hysteresis losses can be complex due to nonlinear history dependent nature of hysteresis. However, several approaches developed mm, have been developed to approximate and stimulate hysteresis in different materials and systems. There are few common methods. Uh, Perisac model. Perisac model is widely used hysteresis modeling technique that represents the hysteresis behavior as a distribution of hysteresis. Hysteresis are elementary building blocks that describe the switch behavior of material. Each hysterion is characterized by switching threshold and weight. By summing the continuum of all hysteresis, the hysteresis material can be appointed. The model requires experimental data to determine the distribution of hysterion uh, for a specific material. Uh, Jealous Atherton model. The Jealous Atherton is another popular method for hysteresis modeling. It is based on the concept of domain wall motion and takes into account the magnetic field, magnetization, and domain wall interaction. The model includes parameters that represent the magnetic properties and microstructural features of material. The Jelius Atherton model used to simulate a loop and calculate hysteresis losses. Okay, Perisac Mavagro May- Mayergov model. The model combines the Perisac model and the Gilles-Atherton model to the dynamic behavior of hysteresis. It includes uh, parameters related to coercivity, remanence, and interaction between different hysteresis. The model provides a more accurate representation of hysteresis losses but requires a large number of parameters. Finite element analysis is numerical technical technique used to solve complex physical problems, including hysteresis modeling by discreting the material and solving Maxwell's equation. Along the hysteresis equation, FEA can stimulate hysteresis losses in various devices. Detailing requires Okay. Detailing requires a fair knowledge of material properties, geometry, and boundary conditions. It's important to note that hysteresis model is an active area of research. Calculating hysteresis losses involves qualifying energy dissipated in material due to hysteresis while um, obtaining an exact analytical solution for hysteresis losses. Some of the few methods for calculating hysteresis losses are area method. The area method is a simple and commonly employed approach to estimate hysteresis losses. It involves calculating the area enclosed by the hysteresis loop on on the BH curve. Uh, on BH magnetic flux density, magnetic frequency of magnetic field, the hysteresis losses per unit time, typically expressed in watts, can be obtained. However, this assumes, however, This method requires uh, a constant hysteresis loop shape and neglects the influence of frequency waveforms. Uh, Steinmetz equation. This Steinmetz equation is an empirical formula that provides an approximation for hysteresis loss. It relates hysteresis loss to maximum flux density, the frequency of magnetic field, and material specifies a parameter known as Steinman's Steinmetz experiment. P is equal. Here you can see the formula which is used to calculate hysteresis losses. P is equal to K, which is basically Boltzmann's constant. Uh, K is typically determined. Okay, K is determined experimentally for specific materials depending on the impurities, heat treatment. F. Okay. Eddy currents refers to the energy losses that occur in a conduction material when subjected to a changing magnetic field. These losses are primarily encountered in electrical machines, transformers, and other devices that involve alternating magnetic field. Eddy current losses are influenced by several factors, including um, magnetic field strength. The strength of magnetic field has a direct impact on magnitude of eddy current induced in conductive material. Higher magnetic field strengths result in higher eddy current and consequently higher eddy current losses. Frequency of magnetic field. Eddy current losses are directly proportional to square of frequency of magnetic field. Higher magnetic field induce more rapid changes on the magnetic field, leading to increase in eddy currents and higher losses. Therefore, at higher frequency, eddy current losses become more significant. Uh, Material conductivity. The electric conductivity of material plays a crucial role in determining the magnitude of eddy current and resulting losses. Material thickness. The thickness of a conductive material affects the magnitude of eddy current. Uh, thickness provided by the material more paths of makes more paths of eddy currents for circulating. Okay. Calculating eddy current losses in precise manner can be challenging due to complex nature of phenomena. However, there are several methods, uh, and approximations available for estimating eddy current losses in various scenarios. Power loss formula. Here you can see power loss formula. P is equal to Ke into B into F square into V square. Here B is magnetic field, F is frequency of magnetic field, V is volume of conductor. Okay, Steinman's equation. As we discussed earlier, P is equal to Kf into Bm square. Okay, excess losses refers to additional energy losses occur in electrical machines beyond the losses account by hysteresis and eddy currents. They These losses are typically associated with factors such as copper losses. Copper losses are due to resistance of conductor materials used in windings and connections of electrical machines. These losses are proportional to square of current flowing through the conductors and can be significant, particularly in high current. Mechanical function, friction, and winding losses. Uh, Mechanical friction losses due to movement of various components within the machine. Okay. Core losses, also known as iron losses, are separate from hysteresis and eddy current losses. They occur due to magnetic core of a machine due to factors such as magnetic hysteresis and eddy currents. Core losses are influenced by frequency and magnitude of magnetic field. Stray losses are basically uh, arise due to leakage of flux in electrical machines. Dielectric dielectrical constants occur in machines that involve insulating systems such as transformers and capacitors. These losses results from energy dissipated as heat. Okay, calculation of excess losses. So we have some of the formulas which we are going to be discussing. Copper losses. Uh, the formula for this copper losses is I square into R, where is the um, current flowing through the electrical machine. R is the resistance. P is the power. Mechanical losses include friction and windage losses are typically estimated based on uh, empirical or measurements. These losses depend on factors such as rotational speed, bearing type, etc. Core losses include hysteresis and eddy current losses, which are discussed earlier. Stray losses are due to leakage of flux due to challenge to calculate accurately. These losses depend on machine geometry, field distribution. Okay. Separating losses in laminated ferromagnetic materials, particularly in context of electrical machine, involves distinguished between different types of losses such as hysteresis losses, eddy current losses, excess losses, and here are few techniques commonly used to separate the losses. Episteme frame test. Episteme frame test is widely used um, method for separating core losses in laminated uh, ferromagnetic material. It involves constructing a test sample known as episteme frame, um, consisting and total core loss separating technique. The core loss separation technique involves performing no load test and load test on electrical machine to measure total uh, core losses and other losses separately. Okay. uh, Here are some of the practical examples. As we can see, transformer. As the transformer induces electricity, as it the voltage stemming from it is step up or step down, either be, but hysteresis, eddy, and excess losses always follow you. Okay, thank you all for spending time to listen my lecture. Hope you subscribe. Bye.